Welcome to part 6 of gravitation. Let's quickly revise the previous lecture. So basically we talked about Kepler's laws, right? The first law is the law of elliptical orbits. All the planets, they revolve around the sun in elliptical orbits. Then the second law is the law of equal areas, right? The area covered, the area swept out by the radius vector, right, is equal if the time interval is the same. So area upon time is a constant, right? So that's the Kepler's second law. And the third law is the law of orbits, which says that t square is proportional to r cube. The square of the time period is proportional to the cube of the semi-major axis of the ellipse. Okay, and we also solved a few numericals related to the previous concepts, that is velocity and time period, etc. Okay, so now moving ahead, today's topic is on energy. Okay, energy of the satellite. Okay, why is this topic important? Because if we want to launch any satellite, or if we want to send a satellite to other planets or probe some, Mars rover or any kind of rover on moon, right? So when we want to send to other planets, we need to know how much energy will be required, right? So when the satellite is in an orbit, what is its energy? If we want to change the orbit, how much energy is required? How much fuel is required? Right? So for all these considerations, the study of energy is important. So let's first begin with understanding what are the different types of energy. Okay? So we have light as a form of energy, right? Light from anywhere, either from the sun or from any other source of light, a bulb or whatever. So solar or light energy. We have heat energy, right? Heat is also a form of energy. Sound is a form of energy. Electrical energy. We have chemical energy, right? It can be any kind of fuel, right? We can consider it as a form of chemical energy. And we have wind energy. Okay, and within the mechanical energies, we have kinetic. Whenever a body possesses speed, right, so we will say the body has kinetic energy. And whenever the body possesses height, if there is an object at a height, then it possesses potential energy. Okay, so these are all the famous forms of energy that we deal with. So out of these, which forms of energy are we going to study for our satellite? Okay, so mainly the two forms of energy that we want to talk about, because the other forms, they are almost the constant, right, almost the same for the life, throughout the life of the satellite. So the two main forms that may vary, right, are the mechanical energies, which are basically the kinetic and the potential. Okay, so we have the kinetic energy and the potential energy. So please note here, potential energy, we are going to discuss more about it in the live class. We are going to talk about what is the meaning of the gravitational field. Okay, the force, we already know the formula for the force given by Newton's law. So force, gravitational field, then what is the meaning of this word potential? Okay, this word potential and potential energy, they are two separate terms. Okay, so we have, or we will discuss this in the live lecture, okay, if not yet. So kinetic energy, the formula for it is given by G capital M small m by 2 times small r. So again, the derivation for this is discussed in the zip file. Okay, so GMM by 2r, 2 times small r, so small r can be replaced with capital R plus h. So as you change the height, right, as you change the height in the denominator, the kinetic energy is going to change. Okay, so that's the kinetic energy. And the potential energy is given by minus, so please note there is a minus sign, minus G capital M small m divided by R. Okay, so if I want to find out the total mechanical energy, right, which we can just in short call as total energy. So whenever we say total energy in physics, it basically means total mechanical energy usually. Okay, so the total energy is going to be the kinetic plus the potential energy. So the kinetic energy we know is GMM by 2R, and the potential is negative, so minus GMM by R. If I do the summation, right, so I can take GMM by R common, and in brackets I'm going to get half for kinetic and minus 1 for potential. So half minus 1 is going to give me minus half, which basically gives me the total energy as minus G capital M small m divided by 2 times small r. Okay. So if you look at all the forms of energy, okay, this negative sign is what we need to discuss now. The potential energy is negative, the total energy is also negative. So what does this negative sign indicate here? So the statement given in the textbook is that the satellite is bound to Earth. That's the meaning. If the total energy is negative, it means the satellite is bound to Earth. It means the satellite cannot just leave Earth and just go away. It can't just walk out and say, okay, bye bye, I'm going to Mars. Okay, that cannot happen on its own. It is bound to Earth. So what does that mean exactly, right? A negative sign and satellite is bound to Earth. Why such a statement is made? So let's take the example of money. We will compare energy with money. Okay. In fact, we have a chapter in physics which is called as work, power and energy. Right. So in that chapter also, most of the MCQs get solved by doing a very simple comparison of energy with money. Okay. So let's say, for example, you have right now with you 500 rupees, okay, in your wallet or in your pocket. So you are possessing 500 rupees. So if I ask you, who gave you this money? Is it your money? Now, assuming you are students of 11th standard, just out of 10th standard, okay. So that, taking that assumption, all right, I can say that probably this money has been given to you by your parents. Okay. So if this money has been given to you by your parents, can I say you are bound to your parents? Right? You are bound to your parents. So if this example still doesn't make sense, then we can exaggerate it. Suppose your parents gave you, say, 20,000 rupees. Okay. So morning 6:45 a.m. just before you leave home to go for your lectures in the morning, your parents give you 20,000 rupees. Okay. And you have 20,000 rupees in your pocket or wallet with you. And the purpose of this 20,000 rupees is, say, these were supposed to be given to your teacher as the fees. Okay, let's assume, let's make this story. So your parents give you 20,000 rupees to give you, to give to the teacher. Okay. Now, your lecture gets over at, let's say, 10 a.m., 7 to 10, 3 hours you had lectures. After 10 o'clock, you come home and you say, you tell your parents that, can you please give me 20,000 rupees more, because I just spent that money. I don't have the money to give to the teacher. I did not give it to the teacher. And so please give me 20,000 rupees more. So if you are going to make such a statement, what would be the reaction of your parents? Okay. So now you can understand that at least financially and even otherwise, you are bound to your parents. They are going to ask you questions. What did you do? Where did that money go? Right? You are bound. Right? So you can't just walk away. You can't just say, oh, I just spent it, just give me more. No, you can't just do that. Right? So the same idea here. The satellite is bound to Earth because its total energy is negative. Satellite simply cannot just do anything independent of its own, unless it earns its own energy. Okay. So say tomorrow you become a doctor or an engineer and you're earning a lot of money, and then you are not so much answerable. I mean, on a moral level, you should be still answerable to your parents, but still otherwise, normally speaking, nobody is going to ask you questions that how much money did you spend, where did the money go, and all those kind of questions which you are asked right now. Okay. So that's the idea. The satellite can't just, if it's orbiting the Earth, it can't just go away. It won't just on its own just start going towards some other planet. Right? We saw that the concept of centripetal force also. Because of the centripetal force, the satellite will keep on revolving around Earth, even if it stops working. Right? Even if the electronic equipment on it stops communicating with Earth, it will still revolve around the Earth because it is bound to Earth. So what needs to be done is you have to burn your own fuel. It has to carry its own fuel and use that fuel, burn it in its own engines, and then go away from Earth, right? If it is launched with a speed more than the escape speed in orbit. Okay, so coming back, so we have kinetic energy, formula for which was gmm by 2r. We have potential energy minus gmm by r. Adding up the two, we got the total energy, which was minus gmm by 2r. Now, there is one more form of energy that we need to discuss, which is very interesting. So, to understand this concept, let us see where do these numbers fall on the number line. Okay, so we have our number line, 0, right, is, you can say, the origin. Okay, so we're just drawing the x-axis. Now, look at this total energy. So, the total energy is negative, right? So, the total energy is negative, so it's going to be on the left of 0. So let us say the total energy is minus 5 units. Okay, the unit, actually it's not going to be minus 5 joules. You know, the unit for energy is joule, because the energy of a satellite is in several hundreds and thousands and, you know, millions of joules. It's going to be of the order of 10 raised to 10 or 10 raised to 9, something of that size. Okay, so let us just round it off and say, give it a simple number, let's say 5 units, but with a negative sign, right? It's minus 5 units. So if the total energy of the satellite is minus 5 units and I want to free it, I want this satellite, which was actually, I just launched it, it was going around Earth, right? So as it is circling Earth, now the next step in its journey is I want it to go towards moon, suppose. Okay, so then I want it to go away from Earth. So I should give it some energy, right? Or it should use its own fuel and burn some of the fuel and get some more energy. So can I say, if I want to make it go towards moon, or maybe make it go towards Mars or towards the sun, right? We have sent recently probes to capture better images of the sun also. So we want it to go away from Earth. We want to release this bondage, right? Because it was bound to Earth. So then how much energy should I give it? Because right now it is having minus 5 units. How much should I give it so that it becomes free from the gravitational influence of Earth? So the answer is, just bring the number, right, to such an extent that this negative sign goes away. Because the negative sign indicates that the satellite is bound to Earth, right? If you had 500 rupees with you, given to you by your parents, okay, so then, you know, you owe 500 rupees to them. Not that they are going to come and ask you, you know, give me my money back. But, you know, for the record, if you are keeping an account, then you owe 500 rupees to them. Now, suppose if you start working, do a part-time job or something, right, and earn 500 rupees. So you owed 500 rupees to them. You earn 500 rupees and give it back to your parents, suppose. Then, in your account, the balance will be shown as 0. Because earlier you borrowed 500 rupees, right? So that would be, let's say, minus 500. If you want to represent it, right, with a sign, let's say minus 500. And then when you earned 500 rupees, that became plus 500 and the number came to 0. So from minus 5, if I want to come to 0, how much should I add? How much energy should I give? So the answer is plus 5. So this energy, which I will give it, right, in order to free the satellite from the gravitational influence of Earth, that energy is called as binding energy. This is the amount of energy needed to free the satellite, because the satellite was bound to Earth. So this word binding, it comes from that word, you know, bound to Earth. Because it was bound to Earth, why? Because it has negative energy. I want to free it. Just make that number, the minimum that you need to do is bring it to 0. You can give it more than minus 5 also, or plus 5 also. For example, suppose I give it 6 units of energy. Right now its energy is minus 5. I give it 6 units. So if I'm going to give it 6 units, then the total will become plus 1. Right? Ultimately it will become plus 1. And positive means it's free. Right? Negative means it is bound. So anything above 0 is fine. But the minimum that you have to give it is called as the binding energy. So it is defined as the minimum amount of energy needed to be given to the satellite in order to free it from the gravitational influence of the planet. In our case, it's Earth, right? So then, as a formula, what would we write for binding energy? Because the total energy is -5 and the binding energy then becomes +5. The minimum that I should give it is +5. So therefore, the formula for binding is simply but just reverse the sign for total. Remove that minus sign. So if total energy was minus GMM by 2R, the binding energy is going to be plus GMM by 2R. Okay, and looking at all of these four, right, we can now understand they are related: kinetic, potential, total, and binding. If you see carefully, so by definition itself, binding energy is negative of total. But look at the formula for binding and look at the formula for kinetic. They are the same. And if binding is negative of total, then even kinetic is negative of total, right? And the potential, if I compare the potential and these other forms, then simply the number 2 is missing. Otherwise, the other things are the same. So what I can get now is a relationship between, first let's talk about kinetic and binding. So kinetic and binding, they are equal, right? See the formula here. Kinetic and binding are equal. They both are negative of the total, and all of these are nothing but minus PE by 2. So if I take this potential energy and divide it by 2, so let's say we divide by 2 in the LHS, so then we have to put a 2 in the RHS as well, right? So 2. So if I put the number 2 in the denominator here, I'll get all these other forms. So that is a very important relationship between all the different forms of energy. Kinetic is equal to binding is equal to negative of total is equal to negative of potential divided by 2. Okay, and please note, very important point to be noted, these formulae, all these four formulae and this relationship between the four of them, this is only valid if the satellite is revolving around the Earth in an orbit. Okay, if there is an object or a satellite in orbit, then you can use this formula. Because in the MCQs, we are going to get questions where they will say there is a satellite or there is an object which is kept on Earth. It is right now on the surface of Earth, and I want to free it from the gravitational influence of Earth. Then don't use this formula, because right now if that object is just lying stationary on the surface of Earth, then its kinetic energy is 0. Its kinetic is 0, and if kinetic is 0, the binding is not 0, the total is not 0. Okay, because the total will then become equal to the potential. The kinetic is 0, the potential is never 0. Okay, so that's why this formula will not be valid for this relationship between all of them will not be valid for an object at rest anywhere, either on the surface of Earth or if it is somehow at rest, in space at some height. Then don't use this formula, right? Use it only if the satellite is in orbit. But point to be noted, the formula for potential energy minus GMM by R, this is valid anywhere, whether the object is at rest or whether it is not at rest. Potential energy formula remains the same. Okay. All right. So there is now an important note again for solving MCQs, because energy related MCQs are quite famous in this chapter. Okay. So very interesting note: energy of a satellite reduces as it comes close to Earth. Okay. If a satellite comes close to Earth, you should understand its energy is reducing. And if the satellite goes away from Earth, the energy increases. Okay. So what does this really mean? Is this really true? So to understand this, okay, let's watch this small clip. So what you understand from this clip now is that the satellite, okay, that whole space station, whatever the satellite plus all the components around it, right? So they were coming crashing to Earth, and initially, before it enters the Earth's atmosphere, at the beginning it is on the boundary. There is that topmost layer where above which there is space, no air, and below which slowly now the air or atmosphere begins to appear. The oxygen and the nitrogen and all the different air molecules, right? They begin to appear. So that at that boundary stage, we can see that that whole satellite was shaking, and as eventually as it came more close, it even caught fire. Why? Because of friction, because of opposition. There is tremendous opposition provided by the air. Why? Because especially it was moving at a very high speed. Okay, so the idea here is that if there is so much of heat generated, so much of light generated, right, then so much of energy is being lost. It is not being gained, right? Energy is being lost. So please note this point again. As the satellite comes close to Earth, right, comes close to Earth, the energy reduces, and as it goes away from Earth, the energy increases. Okay, and this can also be understood, using the formula on the number line again. So the formula was minus gmm by 2r for the total energy. Okay, we are talking about the total energy of the satellite. So on the number line, okay, let's say we have some height, okay, initial height, and at that height, because it's the initial height, let's call the total energy there as TE1. And then again, let's take the same number, let's say minus 5 units. Okay, so at a given height, the satellite had minus 5 units. Now, just as we saw in that video, if that satellite is coming close to Earth, okay, if it is coming close to Earth, then what is happening to this value of small r? Small r is capital R plus h. Okay, so can I say capital R is a constant, but that h, as it is coming closer, reduces. So if the denominator reduces, what happens to the entire fraction value? It's going to increase. So if the number was minus 5, it will now, suppose it comes at half of its initial height, then, right, if small r becomes half of its previous value, then this number minus 5, let's say it becomes minus 10, because it is inversely proportional. So if minus 5 became minus 10, has the energy reduced or has it increased? Because this is the most common confusion which people have. Because I'm saying satellite loses or its energy reduces. Whereas here on the number line you are saying minus 5 became minus 10 as it came close to Earth, minus 5 became minus 10 and minus 15, and as it comes more closer, and crashes onto Earth, then ultimately it will have some minus 100 units of energy, let's say. So can I say that the energy increased because 5, 10, 15, 20 going up to 100, the number seems to be increasing. So yes, 5 is less and 10 is more, but this is where the negative sign carries so much of importance, because 10 is more than 5, but minus 5 is more than minus 10. So on the number line, the previous energy which it had, minus 5 units, is actually more. Out of this minus 5 units, it lost energy because of heat and light, because of the friction from air resistance. And slowly as it came more close to Earth, it was disintegrating also, because that was an uncontrolled entry into Earth, right? So the whole thing was disintegrating and then catching fire and burning away, right? So all that is losing energy. So if it loses energy, please note, it's not going to come close to zero. It's going to go away from zero. The negative sign is what really makes a difference here. Okay, this is a very important point to understand for solving the MCQs. Okay, so now let's move on to the textbook numericals related to energy. So we have 4 numericals left now from the textbook. So let's begin. So question number 4, which are all the numericals. So in that, the third one to start with. Okay. So they're saying calculate the kinetic energy, potential energy, total energy, and binding energy. So all the four forms of energy we have to find out. Kinetic, potential, total, and binding. Okay, so all four forms of energy are to be found out. Then they have given artificial satellite of mass 2000 kilos. So small m is 2000 kg, orbiting at a height of 3600. So h is 3600 kilometers above the surface of Earth, and they have given the value of capital G, capital R, and capital M. These are standard numbers, so we'll not waste space here. We know the values. Okay, so let's begin. So let's first find out the kinetic. Once we get the kinetic, we already know the total and binding, right? And the potential, we can just use the relationship. So let's find out the kinetic energy. So the formula is G capital M small m divided by 2 times small r, and small r is nothing but capital R plus h. So I will say gmm by 2 times. Okay, so all that I have to do now is substitute the numbers. So what do we get? So I will get kinetic energy is equal to, so let's substitute the value of capital G first, 6.67 10 raised to minus 11. Then capital M, mass of Earth is 6 into 10 raised to 24 kg, right? So you don't need to write the units. Then small m, that is a number given to us, 2000. So let me just say 2 into 10 raised to 3. 2000 is nothing but 2 into 10 raised to 3 divided by 2 times. So this 2 is going to get cancelled off. Brackets. Now we have capital R plus H. So capital R value we know is 6400 kilometers plus this is 3600, and both of these are kilometers. Kilometers means it's nothing but 10 raised to 3 meters. So again what happens is this 10 raised to 3 gets cancelled, right? So now we have in the numerator 6.67 and 6. These two numbers are left. Let's adjust the power of 10. So it's going to become 24 minus 11. So 24 minus 10 is 14, and minus 1 more, so is 13. Then in the denominator, 6400 plus 600 will give me 7000, and 7000 plus 3000 is nothing but 10,000. So I have 10,000, that is 10 raised to 4, right? 1000 is 10 raised to 3 and 10,000 is 10 raised to 4. So this 10 raised to 4 will again go in the numerator and it will become 10 raised to minus 4. So all I have to do is 13 minus 4. So that will give me 10 raised to 9 joules, right? This is what I was telling you in the theory also. We were taking on the number line, we were taking 5 units, 10 units, but that number was just for understanding the concept, right? Actual number is not going to be minus 5 joules. It's going to be a very big number like 10 raised to 9, we can see here. So all I have to do now is just do this simple multiplication for which we don't need the log. So I can say 6.67 into 6. If I just do the multiplication, it will be 40.09 is what they are saying. So let me just, you can try it out, right, in your notebooks. Just do the thing. It's a very simple multiplication, okay? So 40.09, and this will be in joules. So if you think about it, if this is the kinetic energy, what can you say about the binding energy? They are the same, right? So I can say therefore the kinetic energy as well as the binding energy Both of them are going to be the same numbers. What about the total energy? So total energy is going to be nothing but negative of the kinetic energy. So minus 40.09. Okay, so we got these two numbers, positive and negative, 40.09 10⁻⁹. What about this potential energy? This still remains. So all I have to do now is this formula. Kinetic is minus potential divided by 2, which we just saw today. So therefore, the potential energy is going to be, bring the negative sign as well as the 2 in the numerator. So it's going to be minus of twice the kinetic energy. So just double this number, 40.09. So you should get the potential energy as minus sign 80.18 10⁻⁹ joules. Okay, so that's our answer for the potential energy. Okay, so this is number 9. Okay, so that is the first one for today. Question number 4, the third numerical. So please take a few minutes, copy it down, pause the video here and write it down. Alright, so now the next one is number 4, question number 4, the 9th one. Within that, planet has mass, so let's say capital M for the planet is 6.4 10⁻24 kgs, and the radius is given to us. So radius of the planet 3.4 10⁻⁶ meters. Calculate the energy required to remove an object of mass 800 kg. So small m is 800 kgs and we need the energy. So required is energy. Okay, so energy required to remove this object from surface to infinity. So this energy is nothing but the binding energy. Binding energy is the amount of energy required to remove the object from the gravitational influence of the planet. So all we have to find out is nothing but the binding energy. Okay, so from the surface to infinity. Okay, so since it is from the surface, I can note down that h is 0. So did they say in this question that this is a satellite? No. If you read again carefully, they are saying required to remove an object. Okay, so what does that mean? That means, if you remember, I told you in the theory, do not use that relationship between kinetic total, right? So we can't use that formula for binding energy. Why? Because the kinetic energy of this object is 0. So hence I cannot use the formula for binding energy as gmm by 2r. I can't use it. So let's derive it then. How do we find it out? Very simple. So if the kinetic energy is 0, what can you say about the potential energy? So I told you the potential energy formula is still valid. So it's going to be minus G capital M small m by R. And if I add the two, I will get the total. The total energy is nothing but the kinetic plus the potential, and therefore the total energy will be, if I add these two, I am going to get minus gmm by R. And if this is the total energy, then how do I find out the binding energy? So again we will use the concept of the number line. If this number turns out to be, let's say, minus 5 units, then how much should I give it so that it reaches 0? Answer is plus 5. So binding energy is nothing but negative of total energy by definition. So this formula is still valid. Okay, B is minus T, that is valid, but BE is equal to KE, and the KE being gmm by 2R, that's not valid. Okay, this formula is still valid. Okay, so negative of negative, so the minus sign goes away and all I am left with is, okay, so the binding energy therefore is going to be gmm by r, or in this case we just have to use the mass and the radius not for Earth but for this planet. Okay, so if you want you can say mp by r. So this small r is nothing but capital R plus h, but the h value is 0, so it's just the capital R. Alright, so what do we get? Plug in the numbers, 6.67. So those values which they had given in the previous question, you see, if you see in this question, they have not given it. It's not printed in the question. So we still should know the numbers, right? So we should just substitute them. 6.67. If you want, you can add a 3 then. 10 raised to minus 11. MP is 6.4 into 10 raised to 24 into small m is nothing but 800 kg divided by capital R plus h is 0, so I'm just going to substitute 3.4 into 10 raised to 6. So let's just adjust the powers of 10 first. So 24 and these two zeros makes it 26. 26 minus 10 is 16, minus 1 more is 15. So I have 10 raised to 15, positive 15, and this 6 goes in the numerator. So I have 10 raised to 15 minus 6. So that will give me again 10 raised to 9, just like the previous question. I'm getting 10 raised to 9. Then the digits which still remain are 6.67, 6.4, 8, right? 800. The two zeros we took away, but the 8 still remains. 3.4. Okay. So now the numerator is more than the denominator. Okay. All the numbers are more than 1. So please pause the video here. Do a simple log calculation. Okay. So if you do the calculation, you should get the number. There is a printing mistake there. It's not 1.004, it's 10.04 into 10 raised to 10 joules. Okay. So please, I'm just using the calculator. I'm not doing the actual calculations. So you please pause the video, do the log calculations and copy it down. Okay, so now question number 4, the 12th one in it. So they are asking, what is the gravitational potential due to Earth at a point which is at a height of, so height is given to us 2 times radius of Earth from the surface of Earth, above the surface of Earth. So what we need to find out is gravitational potential. Okay, so this gravitational potential, we can just use the symbol V for it. Okay. So what is this V? We'll talk about it in a few minutes. So let's first finish the question. They are saying mass of Earth is, so yeah, we know that capital M is 6 10 raised to 24. Radius of Earth, again that is known to us. So instead of 6,400 kilometers, I'm writing it as 64 into 10 raised to 5, right? Kilo is 10 raised to 3, and if I take the 2 zeros from 64, it becomes 3 plus 2, 10 raised to 5 meters. And capital G is again a known number. Newton meter square plus kg by kg square, please note that. So what do you mean by gravitational potential? Actually, this again is a term which we are going to discuss during the MCQs. This gravitational potential is nothing but, if you remember the formula for gravitational potential energy, right? Potential energy, we had minus gm small m by r. So just remove that small m. and what remains is the gravitational potential. So in fact we can say the potential energy, the gravitational potential energy is the potential multiplied by the mass of the object. So this potential is nothing but minus gm by r multiplied by small m. That's what gives us the formula gmm by r. Okay, so why is this negative sign there for potential, and what does potential actually mean? Okay, we are going to discuss it in the live lecture when we do the MCQs. Okay, so for the time being, let's just take this formula for granted, minus gm by r. Okay, so that's it. All we need to do now is, what is this small r? This small r is nothing but capital R for Earth plus H, right? So let me just call it as RE actually, because they have used the suffix E. So RE plus H, but the H itself is 2RE. So if I add the 2, I'm going to get minus GM by 3 times RE. So that's my gravitational potential. So all that remains now is to substitute the numbers. So we will get 6.67, capital M is 624, 3, but I can just divide these two and say 3 2s are, times RE, and RE is 64 raised to 5. So what remains now is, if you want, you can just divide these two also. 2 and 64 will become 32. Right? 2 3s are 2 2s are. So I have now minus 6.67 by 32, and let's adjust the powers of 10. So 24 and minus 11. So 24 minus 10 is again 14, minus 1 more is 13. So I have 10 raised to 13, and this 5 goes in the numerator, becomes minus 5. So 13 minus 5 will give me 10 raised to 8. Okay. But if I write 10 raised to 8 here and check, is the numerator more than the denominator? Then I realize no, the numerator is less. So let's borrow a 10 from here. So let's write it as 6.67 into 10. So when I write it as 6.67 into 10, it will become 66.7. So I have 66.7 into 10 raised to 7. And now I can do a simple log calculation. Keep the minus sign outside, keep the 10 raised to 7 outside. Do a simple log calculation and you should be getting the answer. So 66 by 32. So it should be 2 point something. They are saying it's 2.08. So negative sign, 2.08 into 10 raised to 7 joules. So please check whether this number is correct using the log calculations. And please also note the negative sign is important there. They have just mentioned the answer. They have not written the negative sign. Okay. So please pause the video here, do the log calculation again. Okay, so the last question now for today, as well as in the textbook, question number 4, right? We have done all the questions except for this one. This is the 11th one of question 4. Body weighs 5.6 kg weight on the surface of Earth. So what they have actually given to me is the mass of the object. It is 5.6 kg. Okay. So how much will be its weight on a planet? So this question is not related to energy. This is related to the previous sections that we have done. How much will be its weight on a planet? So what is required now is weight on the planet whose mass is 1/7 the mass of Earth. So I can say mass of the planet is mass of Earth divided by 7, 1 by 7, and radius is twice. So radius of the planet is twice the radius of Earth. So this is very similar to the question there were two questions that we had done in the previous lecture. Okay, so very similar to it is. The only difference is at the end, the units for WP are slightly different, which we will discuss when we reach the end. Okay, so if I want the weight on the planet, okay, all I have to do is basically small m times g on the planet, on the surface of the planet. So because weight is mg, right? Whether it is, if it's Earth, it's mge. If it's the planet, then it's mgp. So how do I get gp? So g on the planet, we know g on any planet, the formula is capital G m by r square, but because it's for the planet, so I'll say mp by rp square. So let's put the values of mp and rp in terms of that of Earth. So mp is nothing but me divided by 7, and rp is twice re. So if I square both the sides, I'm going to get 4 times re square. So I am left with WP is equal to m into, okay, so first of all I have 7 4s are 28. So let me just keep this in the denominator, and I am left with G me by re square. Now look at this number, G me by re square. What is this number, Gm by r square? This is nothing but G on the surface of Earth, which we know the value is actually 9.8. Okay, so till this point the question is similar to what we have done in the previous lecture. Now if you check the answer they have given in the textbook, the answer is given in terms of kg weight. Okay, it's kg weight. So what does this term kg weight mean? So now what we will do is, let us substitute this value of small m. So if I substitute the value of small m, I'm going to get 5.6 divided by 28 times GE. So let's just keep this GE as it is, and let's just calculate this number, 5.6 divided by 28. So it's a simple division, right? 28 2s are 56. So this is going to be 0.2 times GE. So what this means here is, if I want the answer in newtons, I just have to multiply by either 9.8 or maybe if you want to round it off as 10, then I'll get 10 into 0.2 as 2 newtons. Okay, so if I want the answer in newtons, it is 2 newtons. But if I want the answer in this terms of Earth, then I can just say it is 0.2 kg weight and simply drop off the GE. Okay, so by the way, what answer they have given there is again a printing mistake. It's not 9.8 kg weight, it is 0.2 kg weight. So what this means is, if you want kg weight as a unit for a force, weight is a force, right? Then all you have to do is divide by GE, or basically that GE, which is a constant, just remove it, right? So practically what it means is, this object is actually of 5.6 kgs on Earth. The mass of the object is 5.6 kgs. If I take it to a planet, a different planet, this planet, right, who has these specifications, then what happens is the mass of the object going to change? Think about it. Suppose you are 50 kgs, or let's say there is a obese person who is weighing, let's say 120 kgs. There's a really fat person whose mass is 120 kgs. So if he's really fat and 120 kilos, and if he goes to moon or if he goes to some other planet, will his mass actually reduce? Will he become thinner? No. 120 kgs is going to remain the same. That means if I come back to this question, 5.6 kgs is not going to change. It is going to remain the same. What is happening is, when I say 5.6 kgs has become equivalent to 0.2 kg weight, it means that this object is actually, if I lift this object, if I put this object in a bag and I lift it, if I lift the bag, it will feel as if it is 5.6 kilos.
But this same bag, if I take it to this planet and I lift it again with my hand, it will feel to me as if it is 0.2 kgs. That means my hand will feel the same amount of force that I would feel if I lift a 200 grams, 0.2 kgs, 200 grams object on Earth. So if in one hand, if I keep 5.6 kilos, I'm standing on Earth. One hand I have 5.6 kilos, other hand I have 200 grams. Then they, on Earth, they are different weights. 5.6 kilos and 200 grams is different. But this 5.6 kgs, if I take it to this planet, then it will feel as if it is 200 grams. What I feel 200 grams on Earth is what this 5.6 kgs will feel on that planet. That's what it means. Okay, so that's all for today. We'll stop here.